Hey everyone, and welcome to This Explainer. If you are a Class 8 student, or honestly, just someone trying to wrap your head around algebra, you are in exactly the right place. Today, we're going to look at math a little differently, not as a chore, but as a really exciting puzzle just waiting to be solved. We are officially opening up the Detective's Toolkit to master a super essential concept, factorization.
So think about it like this for a second. What happens when you completely reverse multiplication? Imagine multiplication is like building this massive, complex Lego castle. You put all these different tiny pieces together to create one giant structure, right? Well, factorization is the exact opposite. It's the art of carefully breaking that castle back down into its individual core building bricks. It's basically reverse engineering.
And this brilliantly illustrates exactly what we mean. On the left side, you've got multiplication. This is expanding. We take the 3, multiply it across the x and the 3, and bam, we get a polynomial, 3x plus 9. But on the right, we have factorization. We take that 3x plus 9, spot the shared pieces, and simplify it all the way back down into 3 times the quantity x plus 3.
So what exactly are we hunting for here? We're looking for factors. A factor is literally just a number or an algebraic expression that divides into another number evenly. And I mean evenly, with absolutely zero remainder left over. These are the irreducible building blocks of math. Once you break an expression down into its true factors, you've essentially cracked its DNA.
Here is our quick roadmap for today's explainer. First, what is factorization? Second, the 4 key methods. Third, factoring with identities. Fourth, avoiding common mistakes. And fifth, why this actually matters.
Okay, let's dive right into section 1. What is factorization? Finding those building blocks. Let's start with something familiar, just to warm up. Before we even touch the algebra, we really need to understand how factorization works with plain, everyday numbers. Finding the building blocks of a number is something you actually already know how to do. Take the number 20, for example. If we want to find its prime factors, we just break it down into pieces that literally cannot be broken down any further. So 20 is 2 times 10. But wait, 10 can still be split into 2 times 5. So the complete prime factorization of 20 is 2 times 2 times 5. Those 3 prime numbers, they are the irreducible building blocks of 20. Pretty simple, right?
Moving right along to section 2, the 4 key methods. Time to open up that detective toolkit.
Now that we've got the basic concept down with numbers, it's time to shift gears to algebra. There are 4 main tools in your new toolkit: common factors, regrouping, identities, and splitting the middle term. Now, don't worry if this sounds a little overwhelming right now. We're going to scale up from the simple stuff to the complex stuff and figure out exactly when to pull each tool out of the bag.
So the very first tool you should always reach for is method 1, common factors. This is your primary weapon. You're basically hunting for the highest shared term across every single part of the expression. Look at 12x plus 36. What is the absolutely biggest number that divides perfectly into both of those? It's 12. So you extract that 12, leaving you with 12 times the quantity x plus 3. Seriously, always check for this first. Let's move to the next tool and see how this builds. What happens when a single common factor just doesn't exist across all the terms? Well, enter method 2, regrouping. Look at 2xy plus 3x plus 2y plus 3. There is 0 common factor shared by all 4 of those. But if you group them together, say putting the terms with y together as 2xy plus 2y, and the remaining terms together as 3x plus 3, suddenly you can extract common factors from those smaller groups. It's all about organizing the chaos so the shared factors reveal themselves. Now, skipping ahead to method 4 for just a second, splitting the middle term. You'll use this bad boy for quadratics, like x squared plus 5x plus 6. The whole trick here is finding 2 magic numbers. They have to multiply perfectly to make the constant at the end, which is 6, and they have to add together to make the middle number's coefficient, which is 5. So, what multiplies to 6 and adds to 5? 2 and 3. So your answer splits that middle term and results in the factors x plus 2 and x plus 3. All right, on to section 3, factoring with identities. Basically, your math cheat code. Now, what's really interesting about this slide is that if splitting the middle term feels like a puzzle, using identities is literally like having a cheat code. It saves a massive amount of time on exams if you can just spot the hidden patterns. The perfect square identity shows us that a squared plus 2ab plus b squared always collapses down instantly to a plus b all squared, and the difference of squares. It tells us that anytime you see a squared minus b squared, it immediately becomes a minus b times a plus b.
Recognizing these instantly solves the whole problem for you.
Let's actually see this cheat code in action. Look at 49p squared minus 36. At first glance, kind of messy, right? But wait, 49p squared is really just 7p, all squared, and 36 is just 6 squared. This perfectly matches our difference of squares identity. So without doing any complicated math whatsoever, we instantly know the factors are 7p minus 6 and 7p plus 6. I mean, look at how fast that was. Section 4, Avoiding Common Mistakes. Time to meet the villains of our story. Let's talk about the traps. You know, those subtle, sneaky little mistakes that end up costing us precious marks on a test. Trap number 1 usually starts with an inner monologue that goes a little something like this. Okay, awesome. I factored it into 2 brackets. I'll just stop here. The factorization is complete. It is a total false sense of security that hits you right in the middle of a problem. So the crucial point is that you have to keep going until the expression is completely irreducible. For example, say you use a formula and you end up with something like 25 minus p squared. You cannot just stop there. Because 25 is 5 squared, that bracket can actually be split even further into 5 minus p and 5 plus p. Remember, if there's a minus sign between 2 squares, you absolutely must keep breaking it down. Now, trap number 2 is just playfully annoying. It's missing the highest common factor. Say you have 27a cubed b cubed minus 45a to the power of 4b squared. You might look at 27 and 45 and confidently say, oh, I'll take out a 3. But guess what? 3 isn't the highest common factor. 9 is. If you only take out a 3, you're leaving factors trapped inside the bracket, and your answer is incomplete. Always, always grab the largest number possible. And trap number 3 is subtle but completely deadly, forgetting the sign when grouping. When you're regrouping terms, you might pull out the common factors, but then just leave a blank space between your 2 new groups because, well, maybe you aren't sure if it should be a plus or a minus. Leaving a blank space literally ruins the whole equation. You are essentially changing the math entirely. A pro tip, always multiply your groups back out in your head just to double check if that sign should be positive or negative. Finally, Section 5, Why Factorization Matters. Let's bring this all back to reality. So we've talked a whole lot today about x's, y's, squares, and identities. But let's take a step back. Why does any of this actually matter to us? Well, factorization is literally everywhere. On a super basic level, it's how we divide items for fair sharing or budgeting. But on a huge scale, factorization is the absolute foundation of RSA encryption and computer cryptography. The fact that it is really, really hard to find the prime factors of massive numbers is exactly what secures your passwords, your bank accounts, and pretty much the entire internet. Engineers also use it all the time for simplifying complex fractions and division in higher-level physics and computer science. So, as we wrap up this explainer, I really want to leave you with this thought. If multiplication is the process that builds the complex world around us, isn't factorization the ultimate key to understanding its hidden building blocks? You now have the detective's toolkit in your hands. So go out there, look for those patterns, dodge those traps, and reverse engineer absolutely any math problem you encounter.